Okay, for what we have in this section, we have regarding dimension and rank, and we have starting out. Okay, so you have a set B. Okay, where we have among the elements, you have B of 1 going out to B of P, and this is going to be a basis for a subspace H. And we have for each solution set X that we have in H, the coordinates of X relative to the basis B are the weights C of 1 all the way out to C of P, such that X is equal to C1, B1 plus you have your combinations going out to where the last of them will be C of P, B of P, and we have the vector in R of P, okay, where we have, okay, so we have for the coordinate vector of X relative to B, so you have X to be bracketed, and you have B to be subscripted, and this is equal to where we have in the vector, okay, you have, again, we have the B coordinate vector is going to be listing out the weights, okay, first at the top and the last at the bottom. And let's say that if we have as a sample vectors as well as what we have to be X in the subspace H. Okay, so we have so you have a couple of vectors where the first one we have a 2 by 1, so you have the vector, you have 6 2, second we have negative 1 0, and we have in the subspace we have X is equal to 3 12. And now for the basis B, we have, again, consisting of the vectors v of 1 and v of 2. And, okay, it says since v of 1 and v of 2 are linearly independent, okay, so you don't have one vector to be a multiple of the other. And again, B is the basis for what we have in the subspace, okay, which we have equal to the span of both of these vectors. And it says to determine if X is in H, and if so, find the coordinate vector of X relative to B. Okay, so for what we have in the setup, okay, so if we go with the linear combination, so again, we have C of 1 times V1 plus C of 2 times V of 2 is equal to X. And filling in, okay, so you have looking at solving for the weight C of 1 and C of 2. Okay, so we have so you have C of 1, you have 6 times 6 2 plus C of 2 times negative 1 0 is equal to 3 12. And writing as an augmented matrix, okay, so you have the top row we have at 6 negative 1 3, bottom row we have at 2 0 12. And again, as we progress to the reduced echelon form, so I can make the upper left hand 6 into 1, so I can take 1/6 the top row, so I have 1 negative 1/6 and 1/2, and the 2 as the leading element in the second row, I can convert that to 0. Now that I can take the second row elements and take twice the top row elements. So this will be transformed to 0, 1/3, and 11. Okay, so progressing to the reduced echelon form. Okay, I want to convert, okay, the 1/3 into a 1, so I can just take 3 times the second row. So we have 0, 1, and 33 at the bottom. And then to get officially into reduced echelon form, okay, so I have 1 0, and I want to make the negative 1/6 at the top into a 0. So I can take 1/6 of the second row and add to the first row elements. So for what I will have here, it turns out that for the solution matrix, I have 1 0 6 for the top row, 0 1 33 for the bottom. So we have C of 1 is equal to 6, and C of 2 is equal to 33. And so for what we have in this particular case, all right, so we have for the case, again, we have C of 1 is equal to 6, and C of 2 we have at 33. And again, for the coordinate vector of X relative to B, again have the vector where we have C of 1 at 6 and C of 2 to be at 33. All right, now also let's say that if you're looking at finding the vector x that is determined by the given coordinate vector, okay, x of b, and the given basis b. Okay, now in the first example, x was given, okay, but now we're looking for the vector this time around. Okay, so we have for our given basis, okay, we say that our first vector we have at 1 1, second vector we have at 2 negative 1, and again we have for the um, again for the um, coordinate vector of x relative to b, we have 3, 2. So C of 1 is at 3, C of 2 is equal to 2. And so for looking at establishing what we have in terms of linear combinations, so again, I have C1V1 plus C2V2 is equal to x. And filling in, so I have C of 1 is at 3, and I have times V of 1. C of 2 is at 2, and I have times V of 2. And I have is equal to x. So here, looking at the top layers, you got 3 plus 2 times 2, which is 7. 3 times 1 is 3. 2 times negative 1 is negative 2. So we have 3 minus 2 is 1, which will formulate, okay, the bottom row element. And this will be what we have for x. And in terms of what we have, at least in the projections, okay, so we have for just the layout in this particular case. All right, so in taking what we have, looking at the graph itself, okay, I'm just going to add this in. Okay, so we have, okay, just for the layouts, okay, so we're looking at 3 times V01. Okay, so just looking at the progressions, they have V01, 2V1, 3V1, and again we have going out in the direction. Okay, so you have going along x of 1 unit at a time, and x of 2 1 unit at a time, and we have also in the mix, okay, for V of 2, okay, so I have going 2 negative 1, so I have, so again, so I have 2 times V of 2, so projecting out once I have V of 1, and then I have 2 V of 2. Okay, so I have 3 times V of 1 and 2 times V of 2. So just kind of forming a parallelogram. Okay, so I have 3 times V of 1 and 2 times V of 2. And looking at where we have the intersection, this is where we have x is going to mark the spot, and again we have 7 and 1.